Good morning to everyone. Welcome to this dissemination workshop where we are going to introduce the position papers on safety and education and skills. My name is Roberto Pacios from CIC Amietszajew, and I will be hosting the first part of the session. For the first part of the session, we have this agenda, this scheduled. At the beginning, we will present the safety position paper by Guillaume Thenaisie from VITO. Then we will have a short presentation about the progress on standardizing safety for stationary batteries energy storage systems. And then we will have the opportunity to ask questions. Then for the second part of this, the first session, we will have a roundtable discussion about new approaches to develop enhanced safety material cells and battery systems. There will be three short presentations on different aspects, on different topics. And then we will have at the end of these three presentations, we will have the opportunity to discuss around the table and also ask some questions to the speakers. It's a pleasure for me to host this session. I would like to take the opportunity to thank once more, especially the speakers, for the active part within the task force, the safety task force. And Guillaume, the floor is yours to introduce and to present the position paper. Thank you very much to all of you for joining.
Thank you, Roberto. Is the screen visible for everyone?
Yes, it is, yes.
Perfect. So, hi everyone. So, my name is Thenaisie Guillaume from VITO, as introduced by Roberto. We are going to discuss today about the position paper on the safety task force. So, the chair, Daria Giovanacci, I hope I will not butcher any name. The co-chair was Maros Harama, technical coordinator, Roberto, that you already seen, and me. So the scope of the position paper, or the main objective, were double. First, we wanted to identify the coming safety challenge along the entire battery value chain, and not just, for instance, the fire that you see in the news on the end user part. And second part was to give some recommendation on the research and development effort to tackle those. It's important to know that we have a major focus on lithium-ion challenges because this represents the main bulk of the battery market today. But the position paper acknowledges also new and emerging technology. For instance, there is some quick discussion on the flow batteries and new chemistries. So our position papers is structured in two big parts. One part is analysis of the safety along the value chain, where we discuss the safety from the material level all the way up to the end of life. So we discuss the manufacturer, but also the research and development, because the safety in the factory versus the safety in the lab is not exactly the same. There is discussion also about the different level of safety, because it needs to be implemented from the module down to the cell. The safety also at the use phase, mobility versus stationary, do not imply the same risk, and therefore the end of life. The second part is the interconnection, which we really think was something that has been brought up in this position paper compared to the previous part, was an insistence on how safety needs to be combined with other topics, such as digitalization, sustainability, and education, because without those three interconnections, safety will not reach its function. We want to highlight some specific cases. So among the discussion we had within the position paper, it appeared that there is an increased need for digital, non-destructive testing and sensing solution that should be the driver for improving safety at every level. As of today, those are not enough developed, neither in academic nor in industry in terms of tools, not in the research part. And also beyond the lithium, there was a big safety consideration for flow batteries due to the discussion along the electrolyte issue, also the understanding of and behavior of the other components that was not fully clear for everyone, and the need for additional tests to understand the behavior of low battery stack, which seems to be quite an open field today. The main takeaway or recommendation that we concluded was, first, it's really important to have a global view on safety and not just a very focused view when we only care about the part that directly addresses us, because safety is really something that goes over the entire value chain. Another part that was important was to establish and maintain somehow a database of battery-related incidents, because it's really a plus for the entire community when those databases are available, because it can be used as a way to check whether new systems are safe-proof compared to historical incidents, which we do not have yet. Also, we need to develop some safety KPI more than just the one existing today, such as no fire, but we need to develop them and bring them all the way to standardization, because it's still a bit fuzzy also today. And one of the key elements also was there is a need to educate and train the workforce on all the aspects of safety, because this field is fairly new for all industry, the battery as it is, and the safety training is really lagging behind the first imperative of productivity, which means that there is a big need to train the people. We have identified some elements, such as the new sensing technology that we discussed, the demand for testing that is rising and will keep rising, the fact that testing must be complemented by modeling, which is also a bridge to establish, and the fact that new emerging technology might solve some hazard on one hand and bring new one on the other hand. And those 4 points will require new R&D efforts. There is an important note. The introduction of robotic and automation might improve safety at different levels, for instance, production of end of life and second life, but it's not clear yet how much can this be improved, since the entire safety landscape needs to be fully defined from the standard we discussed just before. I would like to thank the contributing member and everyone else who took part into these position papers. And that's all about the introduction. Thank you.
Thank you very much, Thenaisie, for this very nice and clear presentation. And now we move to the following contribution to this dissemination workshop. Franco di Persio from CIRCE is going to give us an overview of the progress on standardizing safety for stationary battery energy storage systems. So, Franco, whenever you want, the floor is yours.
Okay, thank you, Roberto. I will share my screen now. Let's see if it works. Okay. I think you can see now, I hope. I don't know.
Yes.
Yes, but
right.
we see the PowerPoint application.
Right, so let's see if I... Okay, now should be in the presentation mode, I hope.
Not yet. At least on my screen, it takes a while.
But you cannot see the PowerPoint either?
Yes, I still see the PowerPoint application.
Okay, strange. Okay, so let me see. Oh, okay. Okay, now probably it's the same.
Yeah, it's the same as
Sorry
before.
about it.
Yes.
So I will stop sharing. Again, I will share. Let's see if now it works.
Yes, now we can see the full presentation mode.
Good, perfect. Thank you. Okay, so good morning to you all. Thank you to Beppa for inviting me today on this workshop. So today I will present on the process on the standardization of safety of stationary battery energy storage system that are we will see are included in the battery regulation, the 2023 1542. So we will go through some definition, just few definition of Article 3 of the battery regulation, considering the repurposing or preparation for repurposing, what is known as a second life and second use, since those are a typical stationary application. Then we will look at Article 12, which is addressing the safety of battery energy storage system, stationary energy storage system in the battery regulation, and look at the safety parameters that are introduced by the regulation. And then we will look at the progress within Sense and Elec standardization works. Okay, let's see. Okay, just a few words on CIRCE, where I belong to, my company. CIRCE is Technological Center. We are located in Spain, in Zaragoza. Our main objective is to transfer innovation and knowledge to the industrial sector. We are participating in several European projects, national projects, research innovation projects, and our main field of works is the energy sector. So we're looking at the generation, transmission, distribution, energy, and of course also how to use this energy. So looking at the efficiency in the industrial and commercial sector, and of course also at the circular economy and sustainability aspect. Let's enter now in the core of the presentation. So the battery regulation, there are three definitions that I think is important to address here. Okay, the definition of battery. Okay, we know very well what is a battery. It's included the definition in this battery regulation. But it's important to know that they include as a battery also the battery that has been prepared for reuse, repurposing, or remanufacturing, which is meant also then electrical vehicle second life battery. Then the industrial battery, which basically include the repurposed battery and any stationary application. Battery for stationary application is intended as industrial uses, industrial battery, which is then defined in the article, in the definition point 15 on definition of stationary battery energy storage system. So this is important not to give an overview of what is intended by those terminology. Now the Article 12. So Article 12 is the only article in the battery regulation that is generally addressing the sustainability of battery, that are addressing the safety. Important to mention here that this safety aspect addressed in the battery regulation are intended for all safety aspects that are referring to normal operation and use of the battery. So it's not including transport, not included the installation. That is important. Also, quite challenging and relevant is that the battery regulation define a date, so it's in 2 months' time, basically, that any manufacturer or economical operator that put on the market a stationary storage system for stationary application need to provide a technical documentation which demonstrate that all the battery has been successfully tested for all the safety parameters that are defined in Annex 5. We will see then those safety parameters. And also should include a risk assessment analysis looking at the safety hazard for the stationary battery energy storage system, eventually addressing hazards that are not included in the Annex 5, and all the mitigation instruction for those identified hazards. Also important that, as in several articles appear in the battery regulation, the Commission will adopt delegated acts to update the regulation, which means also all the harmonized standard that should be adopted in order to comply with this regulation. Nowadays, the safety standard or harmonized safety standard for stationary battery system are not still yet are not existing yet. So that's why we will go through then afterwards what are the works of Sensenelec. Just before I give a fast overview, what are the safety parameters that are addressed in the Annex 5. We will go through them. There are 11 safety parameters. So thermal shock and cycling, basically to assess what are the behavior of the battery when we expose the battery to extreme and sudden change of temperature, basically mechanical to check the mechanical integrity of the battery due to this change in temperature. Then the external short circuit protection, we are looking at the ability of the cell to withstand current without reaching hazard situation. What are the protection of the overcurrent situation, hazard situation, which could generate at cell level heat or electrical arcing. Then overcharge protection. Okay, the hazard of the overcharge is the composition of electrolyte, cathode-anode breakdown, the composition of solid interface, separator degradation, lithium plating, so on. So basically, the test should include what is the charging rate and the final state, reached state of charge, and can be controlled by voltage or current control. Then we have the overcharge protection. Basically, the main hazard is the reversal polarity that could lead to oxidation of anode, current collector, and the plating of the cathode side, and then the information, which lead then to the short circuits. Then we have this other, the over temperature protection. Basically, we are looking at the protection against the internal overheating during operation. And then we have the thermal propagation. So we know everyone here what is a thermal runaway in one cell that could cascade to through the entire battery. Here, the battery regulation is referring to the other standardization works going on in the ISO and in the UN Global Technical Regulation. We know very well that there is R100 for electrical vehicle battery, and there is also the R100.2, which is addressing the thermal propagation, mainly the initiation of the thermal propagation testing. Then we have mechanical damage by external force, basically to see what are the potential hazard situation due to the mechanical stress due to the accidental impact to the system. Again, here remind that this is referring to the real life use, to the user, to the operation stage of the battery, not in the installation or transportation. Then we have the internal short circuit. Basically, we are looking at okay, that is the typical initiation of the thermal runaway. So basically, we are looking at a different scenario through this test. So possible electrical contact between cathode and anode, current collector, or aluminum current collector anode. So each of those are different contact resistances, so that's are to be addressed in this test. Then we have a thermal abuse. Basically, we are exposing the battery system to certain temperature, elevated temperature, and see if it can trigger the decomposition reaction, a thermal runaway. Then, similar to this, but with the fire, then we have the fire test, exposing the battery to fire. What is the resistance? How long it can take not to resist to the exposure of fire? Then we have emission of gases. So we know very well that the component inside the battery can be really hazardous materials, especially if the gas that could be released from those components. Either by venting or if there is a breaking of the case of the battery, could be also release of electrolyte that could lead to evaporation of organic components that are extremely toxic. So in each of those tests that we are listed, we are just listed from point 1 to 10, all the assessment of the toxic gases emitted should be also performed. So that is a short overview of all the safety parameters that are addressed in the battery regulation. And as we said, the European Commission has empowered in the battery regulation to provide a delegated act to update the battery regulation. In this case, for example, including harmonized standard that could be used for the assessment of those or for use it to perform those tests that we just mentioned. Now we have there is a standardization request that the European Commission has made to the CENSENELEC. There is a working group within CENSENELEC that are addressing those standardization work. And the work is going on actually. Important to know that the delegated acts are normally usually taking 1 year for the finalization of the standardization works. So that means that there will be, as we mentioned before, there is already a requirement for the battery manufacturer, stationary battery manufacturer, by August 2024 to provide documentation that actually are not still their harmonized standard. So it will be, we will see, as we see here, there will be a lagging periods of where the things will be not completely defined, let's say. Because as we see in the last point 7, you can see in the table before 0.7 that are addressing the safety of the stationary energy storage system, as well as the safety of repurpose system. That is most of the case is the second life application. That is foreseen the deadline for adoption of the finalization of the standardization works and the definition of harmonized standard is the June 2026. So we are 2 years will be a periods of let's say not completely defined context for those standardization tests. Basically, is of course those works in the CENSENELEC are not works that are made from the scratch. So we have several standards that are let's say used as a starting point. For example, the ESC 62619 that are referring to industrial application. So this basically the works of CENSENELEC is to adapt this standard to the battery regulation and then introduce in the standard on annex, defined annex ZZ, to inform to what extent this standard cover the requirement of regulation, in this case, the battery regulation. So basically, the objective is to make this standard, let's say, as a product standard. So specific application may require specific tests and checks. So front of the meter will be one situation. Behind the meter, for industrial, commercial, residential application, also can be can require specific test. So that's the basis would be used at the ESC 62619, but then things need to be adapted. Also considering that some tests that are foreseen in the battery regulation are not included in this standard, like for example, fire testing or emission of gases. So there is work going on those aspects. Let's see, right. Okay, that is just to give you an overview what are the tests included in the ESC 62619. So the pass file criteria need to be adapted, as well as the test unit. So cell level, most of the tests are conducted in cell level in this standard, while the battery regulation may require the system level. Then also no venting should be included in the pass file criteria for the emission of gases requirement. So I leave here this without entering too much in detail. This table where there is the correspondences between the test in this standard and the safety parameter included in Annex 5, and there are safety parameters that are not included in this standard. Then we have also another aspect that is the repurpose battery, so second life electrical vehicle battery. That is add more challenge to the works, let's say, to the standardization work, because in case of a repurpose battery energy system, there are several aspects that need to be addressed, like the heterogeneity of first life, which lead to the difficulties to consider as a new product, so to adopt the same standard as for the new product for a repurpose product, which is not the case, because we have not on the back, we don't have a standard, let's say a production process or industrial process properly addressed, which means that there is heterogeneity, and we cannot be sure on the performances or the safety parameter of the repurpose battery. Then there is also lack of information. We know that the battery passport obligation will become compulsory from 2027, so will be a lagging period of where we will deal with this lack of information. Also, OEMs normally are testing to the system level, and then are using testing that are referring to the cell level. So the module, which is the element usually employed in the repurpose system, remain a bit on the limbo. So all those things could force the oversight safety concept by the operator, economic operator dealing with the repurpose product, which can lead to an increase in cost. So that is something that has to be considered. Just finally,
Franco, there are only a couple of minutes left.
Yes, this is the last slide.
Okay,
so basically, yes, that is just for the repurpose product. What are the status actual nowadays in the working groups in the Sensenelec? There is this standard that existing in German standard, which has been taken as main starting point for the repurpose product. And then, of course, there is also, beside the Sensenelec works, there are also ESC standardization works going on the repurposing product, which is the AC 63330 and 63338. but unfortunately those are not when they are the intention were to address the safety, but unfortunately because of this type testing problem, the heterogeneity of products, of repurposed product, are made that those standardization effort are not really addressing properly the safety. So that's actually the status. So that's all from my side. Thank you.
Thank you very much, Franco, for this overview. And now we have some time scheduled for questions and answers. So for Franco, about the overview he has just given, or if you have also any questions about the safety position paper. By the way, I copied the link where you can download all the papers from all the task forces, from the transversal task forces from the chat, so you can directly access to the position papers. So are there any questions? You can raise your hand, or you can also write the question in the Q&A tool of the meetings application, of the Teams applications, as you prefer. In any case, we will send you or we will make available all the presentations after the meeting, because I saw some comments and some questions about this, where and when presentation will be available. We will send you the link after the meeting.
I think there is a question by Edel on the chat. Could be. Which topic do you think is the most important to address with research? Okay, I don't know if that is referring to the position paper.
Edel, could you clarify if your question was to Franco about his overview, or if it was about the different task forces position papers? Yes, Edel, go ahead, please.
Yeah, she cannot unmute. Okay, we can go to the other test. Will specific trace address specific type of battery? Probably that's this question from Antonio Areosa Martins is for me, I believe. Okay, that will be an adaptation of the existing standard to specific application. That's true. So it's not the same to test a residential stationary system compared to the stationary to grid level stationary containers. So as need to be the tests are the same, and the way they are addressed, the pass-fail criteria could be different. I don't know. That's if it I answer to Antonio. Then there is Siebold Mulder. Are we working with a Chinese partner on this issue? No, that is Sentinel working groups, so these are European level. But there are for the thermal propagation, you know, the UN technical regulation, which is include also R100 for electrical vehicle. That is global, so there is the participation of Chinese within others. There will be from the States and Japan, Korea, and so on, but not specific on the battery regulation which is need to be implemented in Europe. Indeed, the Chinese manufacturer want to put on the market, in the European market, their product need to let's say comply with this regulation, but they are not participating in defining testing.
We have another question for Edel. I would like to ask someone at the organization if it's possible to unmute participants, because at least from my side, I can also unmute participants. So Spiridon maybe, or someone from Zavala, is it possible to unmute participants and give the possibility to ask directly?
Hi, Roberto. No, I don't have this possibility. Maybe Zavala.
Now it's unmuted. Now you are
I
unmuted.
think
Now you can ask.
Perhaps this is working now.
Okay.
Can you hear me?
Yes, we can.
Yes.
Excellent. I'd like to kind of understand what particular topic with regards to stationary storage and what you've given the overview on now, what specific topic do you think would be the most impactful to carry out research on? Are we really concerned with looking at the safety, for example, in lithium-ion or flow batteries, or which issues should we address first? Which are the key ones that will be most impactful that we need to address?
Okay. Probably the one aspect that still is not it requires a lot of investigation is the thermal propagation and how those tests can reflect the real situation. Because in order to initiate a thermal propagation, you have to initiate an internal short circuit, which means that you have to manipulate the testing sample, and any manipulation introduce some aspects that are not in the real life, because in the real life the internal short circuit happen without manipulation. There is some effect or whatever. So that is an aspect that I would say that are require specific attention. Is important, I believe, that could be addressed by research and innovation.
Thank you very much. Thank you very much once again, Franco, for your overview, and thank you very much to all the people who contribute with questions. Now we have to move on to the second part of the dissemination workshop, the thematic session. This session will be around new approaches to develop enhanced and safety material cells and battery systems. As I said at the beginning, we will have the opportunity to listen to the three speakers, and then there will be no questions between presentations, and then we will have at the end of the third presentation, we will have some time scheduled for a roundtable discussion and also a slot for questions and answers you might have. So thank you very much to the speakers. I will also thank them at the end of the session, but it's a pleasure for me to have them on the panel here. So the first one is Enric Guillaume from Efectis, and he will be addressing some what kind of fire and explosion risks we have in batteries. So whenever you want, Enric, the floor is yours. Thank you very much for taking part in the dissemination workshop.
Thank you very much. So,
now you have to unmute it because I muted everyone and Enric, and now you have to unmute yourself again.
Yes, sorry.
Okay.
So thank you very much. So I will try to go quickly on the topic with following, in fact, the different elements of the roadmap and giving our view on that. So just a few words. Efectis is a company that is leader in fire and explosion safety engineering, and so we do only fire and explosion, but we do that for everything and not only for batteries. And it gives us sometimes a point of view that is, I will say, more general. And so I will try to present you this point. So first of all, we have to understand what is a battery fire. So it's not a fire. It's really something very specific, because you have everything inside the battery. You have the fuel, you have the oxidant, you have the energy that is available, and so it makes a lot of things different from the classical fires. You have also well-known the initiators, so we could deal with mechanical stress, with thermal stress, overcharging, over-discharging, and so on. But in the end, we have an initiator and we have a history of the fire. So it means that it makes a scenario. And everything about fire safety is scenario driven, so we will see that later. For sure, the influence of the battery chemistry matter, but I would say if you take an example of a car or a BASS, when you have a fire, when the firefighters arrive, they don't know what will be the chemistry and so on. So they have to focus on what is the global performance of the system, and without this knowledge of the details. The state of charge is also a key parameter. It doesn't change necessarily the quantity of energy that will be released, but it changes the heat release rate, so the way, the speed of release of this energy. And this is what we see at cell level in the curves that are just on the right. And so all this make a question about strategy for firefighting. And so what are the scenarios, how we can suppress a fire from batteries and so on. And in fact, you will see that in the end, you cannot really suppress a fire of a given cell that started or a given module, but you can limit the propagation to the other parts of a battery. So this is a multi-scale problematic. You have to think about criteria at cell level, at module level, at pack level, and also consider the environment. When we deal with BASS, for example, if they are included in a building, you cannot omit what is the regulation for the building and what is the compartmentation of the different parts of the building, because we have to have an holistic approach of the safety for that. The quality of components is something that is a key point, and quality of BMS for sure is one of them. So it's not only just a question of chemistry, of cell, it's also of assembly, of architecture of the battery, of quality of BMS, and how you manage the thermal runaway. So how do you separate the different elements inside your battery? How do you evacuate the pressure if you have accumulation of gases and so on? And this is what we see in different tests we perform. So if I start with safety in cell pack system design and manufacturing, so here we have active materials, active inputs, active outputs in the process. We have a very important value of the raw material stock. We have a very important value of the process, and the value of the production itself and the storage and all the logistics after. So we have some histories of logistics problem, and how to store batteries, how to protect a plant, for example, is very, very important. It has to be think at each step because of all the value of the chain. In the use phase, in mobility application, so it's application driven, including the different scenarios again. So if I take, we dealt just before about ECA Air 100. ECA Air 100, the scenario, in fact, for fire, it's like a fuel spillage on the ground. And this is how the battery reacts to that. So it means that it is well adapted to a hybrid vehicle or to a mixed park of vehicles, including fuel vehicles. But what happens? Is it the scenario if you have 100% of electric vehicles present? It doesn't focus also on the fires from the inside of the vehicle. It doesn't focus on the fires from the inside of the battery. So you just have a conformity in the end, but to one family of scenarios, and you not cover the risk with all the possible fires. There's from different studies we start to have now, if we deal with especially individual vehicles, we have no big difference between fire behavior of internal combustion vehicle and an electric vehicle. 80% of the fire load comes from the vehicle itself, from the materials, the different parts, including the case of toxic gases, because if you burn, for example, climatic liquids, you release also hydrogen fluoride. So it's not so simple. But we start to have data collection, and data collection seems to be in favor of less risk of fire start for electric vehicle compared to internal combustion vehicles. And here I just plotted Australian statistics, but it just gives an idea also of the evolution. And the evolution of the number of fires is really following the evolution of the number of vehicles, but the rate of fires per million vehicle is very low. And there are still questions to solve in terms of research for fire safety. For example, in car parks, is the propagation from vehicle to vehicle different or not in a car park situation for electric vehicles? And especially, it's a question of jet flames that could occur in such kind of scenarios. In use phase in stationary applications, then we deal with BESS. So the question is how to manage the design of this BESS, how to design the ventilation, how to design eventually gas accumulation, evacuation of the pressure if there's a thermal runaway, and a distance between the elements. And all this can be designed, can be calculated with some limits. So at present time, in terms of research, we are working a lot on how to model properly battery fires at this scale, because it's not so evident. You have something like a metal fire at the basis, something like a more classical fire on the top, and you have to calculate the safety distance with these different emittances, so different emission powers of each part of the flame. So it's a multi-scale problem. Safety in end of life. So it's again scenario driven. So it could be post-accident battery fires. It could be normal life. It could be abuses. We have to consider second life, use of batteries in less constrained smart grid configuration compared to electric vehicles, for example, in terms of charging and discharging. And ultimately, we have more and more studies and projects on using battery residues as a source of minerals to finish the loop and to restart as raw materials. And for all these items, each step, we have to think about the environmental impacts, including environmental impact in case of fire. So it's very quick presentation, but it's to give just a good overview of that. We have to consider upscaling from cell to pack and to battery with key challenges at each step. Solutions that work at cell level are good, but they don't anticipate what will happen at battery level or at the end use condition. For example, a car or a BSS in a building is not a BSS alone or a car alone. You have to consider also the interaction with the environment. We have to consider fire safety in the system in this end use environment. So we have to think about if you use, for example, battery system to replace electric groups in hospitals, you have to take care about all these scenarios and not only thinking about the battery. We have to develop common European standards on fire safety, not limited to pass-fail homologation tests. So in the previous presentation, we saw a part of that. We still have a lot of standards to develop at present time. So this is something we have not to omit, and we have to make some interactions. For example, the one I mentioned about BESS, we have to make that in interaction with NTC 127 that deals with construction and building at European level. So we have such kind of interactions also to develop to have a safe system in the end. So it's very short introduction, and I will be very happy to answer to the questions at the end of the session after the two other presenters, I think. Thank you very much.
Thank you very much, Eric. It was just on time, so thank you very much for being on time once more. Now we we move to the second speaker, to Amietszajew from the University for Conventry University and also from the Faraday Institution, who is going to tell us about the main challenges on advanced battery diagnosis regarding safety. Tash, whenever you want, the floor is yours.
Hi everyone.
Thank you very much for
I hope you can hear
taking
me.
part in the workshop as well.
Can you hear me well?
Yes, we can, yes.
Brilliant. Let me go into the presentation and share it. And you should see the presentation. Yeah, I hope it works.
Yes, we see the
Brilliant.
presentation.
I'll try to squeeze into 10 minutes. I see there's also we're slightly behind the schedule, but yeah. So from the safety perspective, basically, the biggest challenge is, I would say, that we have this black box concept. So we'd like batteries to work like a magic box that provides power, but they're not. What's inside the battery is very complicated, and I wouldn't want to tackle it alone, but we have this European community, and we get together to address all these aspects of battery degradation, battery safety, battery state of health, the state of charge, and estimation of all these aspects. The reason why is we can either go under or over. If we go underestimate, we have cases like Nissan Rapidgate, where the second generation Nissan Leafs were performing worse than first generation on the road because of overestimation of battery temperatures that led to cutting of the charging current. And then it turned out it was a software update could fix it, which means that this is a diagnostics and model issue, that it was fixable by adjusting the battery model underlying on the BMS. And if we underestimate, then obviously we end up with this, which just a colleague just before me explained, it's not optimal, yeah? We tackle, in this position paper, we identified 4 main stages at which safety is critical, and then the safety of it all, obviously. And each of these can benefit from good diagnostics. Starting maybe at the material/cell level, there is a big increase now in ultrasound technologies around end-of-line testing, where we did a curious study where we supplied some batteries that had implanted faults, like uncoated patches or slashes across the electrode, and our collaborators could detect where the mistakes in the cells are using ultrasound testing. So there is a lot of work being done on end-of-line testing on battery defects, which helps massively with battery safety once they're deployed, obviously. On the cell itself, thermals are a very big issue. We know that it's most spectacular when it fails. And we know that cells have thermal variance, but quite often we don't know how much. We focus on the fact that there is some variance. We do a pseudo 2-dimensional models or lump models, and we don't really observe what's happening inside. But there's a lot that can be done about this. We develop sensors that go inside the batteries, but we're not alone. There's groups in France and Germany that do that. Where we implant various sensors inside batteries, and we can have a look inside. So, for example, looking at standard lithium-ion 18650 batteries, commercially available, we can do some testing where we observe the difference between the core and the surface skin temperature during cycling. Some batteries, very nice, very, very low gradients, 8 degrees, let's say. Some other models, you can have more than 20 degrees variance. So you think that, let's say your electrolyte is stable to 60 degrees, you have a thermocouple on the battery, and your system thinks, yes, the batteries are okay, they're under 60 degrees. But inside the battery, you may be hitting 80, which would be pretty significant damage to the electrolyte at this point. Without proper testing, without proper validation, you really don't know that is happening. on the later down the line, something like this can be implemented into an actual product. We had a project with a company called Breathe where we developed these internal diagnostics. They used it for the BMS system, and you end up with very, very nice models that actually predict what's happening inside a lithium-ion battery. So you can really utilize the data you can generate with advanced diagnostics and end up with a much better BMS control. At the end of life, diagnostics are extremely important because, as we know, there's many quite risky aging mechanisms, such as lithium plating, where you have dendrites and you end up with shorts that can lead to catastrophic failure. I had a student working on using fiber optics. I know there's a group in France that does similar, where the concept of optical prism and a evanescent wave excited by light going through the prism can actually detect various metal ions. We tuned it for lithium, and we were able to observe lithium accumulation on the electrode. So using technology like this, you can observe whether your lithium is getting into the electrode properly, whether you end up with lithium plating, whether you're overcharging, undercharging, and you plots that show you lithium distribution across the electrode, for example, which is very informative. And then you can obviously feed it into your models and inform the battery control system. One of the biggest problems at the safety at end of life is it takes time, and it's because of that it's also very costly. So we need some quicker while reliable testing methods. There is various screening papers where people try to tackle this problem. One of the ways that we try to do it is using harmonic responses. So what you do is you utilize the good old EIS. You deploy it on a cell during usage, and you end up with harmonic distortion patterns which grow with aging. So you don't have to stop the cells. You can run it as the cells are running. It's a very quick test, and you end up with a good indication of state of health as the harmonic distortion increases with the cell degradation. So there's ways how we can test batteries much quicker, how we can test them in usage, which provides us with a good information for then second life, end of life decisions, whether we can reuse it, whether it's safe, whether they have any health left in them. And we shouldn't forget about the now booming machine learning and AI, where we can use the newly collected data from inside the batteries or using some novel diagnostic methods and feed into models that can, using neural networks, using distributed deep learning, we can end up with diluting which electrode degradation mechanism we end up with in a battery, depending on the data we get out of it. And we can use it for safe lifetime extension, either on the BMS system or quite often using a digital twin, where the diagnostics run separate because they need more computational power, and we end up with a control algorithm that can increase performance, that can extend the lifetime and naturally increase the safety. So there's many methods. They usually work in tandem. But the key message that I want to say today is that basically we need your inputs, we need your solutions for it to work together, and we need innovation and skills on the battery safety side. It's a very important subject that is difficult to tackle because of the variability of the chemistries, because of the variability of the cell formats. So we can basically take all the help we need with that aspect. Thank you very much.
Thank you very much, Tas, for this very interesting presentation. I'm sure there will be plenty of questions for you at the end of the session. And now we move on to a slightly different topic, which is redox flow batteries. I would like to mention that there are some aspects that are newly covered regarding safety on redox flow batteries in the updated position paper. That in the past it was strictly focused on lithium-ion batteries, and this year in the update we already introduced some new aspects regarding some other technologies, and one of these technologies was redox flow batteries. So Edoardo from FPK is going to comment on the main safety issues related to redox flow batteries. So thank you very much, Edoardo, for taking part in the dissemination workshop, and the floor is yours. Thank you.
Thank you very much, Alberto, for the introduction. Just give me 1 second, I will show the screen. Can you see it in presentation mode?
Not yet. I see the PowerPoint application. Ah, yes, now it is, yes.
Now, yes?
Yeah.
Perfect. Thank you. Good morning, everybody. I'm Edoardo Macchi. I'm the head of the unit Battery and Electrification at Fondazione Bruno Kessler. Today will be very, very brief, since we are a bit late, and to introduce you to some safety issues related to reduced flow batteries. Also talking about what are the gaps that we need to fill in to have an improved safety and improved analysis regarding also the upcoming solution that are currently being developed. So reduced flow batteries, they're very different from lithium-ion batteries in terms of technology. They have several advantages since we can, let's say, split apart the energy content from the device that is producing, let's say, the power. So for reduced flow battery, as most of you already know, the electrolyte is stored in big tanks. These, of course, make this kind of system very safe, and the thermal runaway is not an issue for this kind of system. However, there are other type of hazard, mainly the chemical hazard, since the electrolyte are in most cases corrosive substances, and in some other cases there are also other risks to be considered. The risk that the hazard that are mainly present in reduced flow battery are electrical risk, chemical risk, so chemical exposure. In some flow batteries, not all of them, but in some, there is also a fire and explosion risk. And also similarly, some of them have also an environmental risk to be considered. So as you can see, I mean, it's quite clear that the hazard at present are strongly dependent on the specific chemistry, on the specific flow batteries. So a dedicated hazard and mitigation analysis is required. We can have some flow batteries that have just chemical risk, chemical corrosive risk. Most of them have this kind of risk since the electrolyte needs to conduct well current. Some, like vanadium flow batteries, have an environmental risk regarding pollution of environment and or let's say also the life or the organism of the environment. Other instead, like zinc bromine flow batteries or other flow batteries employing bromine, have also a toxic risk that has to be well assessed and evaluated. I mean, it's not like having a risk is something that make this technology unsuitable, as we are here discussing, but it has to be managed in an appropriate way. Similarly, flow batteries employing hydrogen have also an explosion risk, since we need also some pressurized storage for hydrogen to be used in the flow battery. The threats are of different type. So we have, of course, a main risk related to the type of electrolyte that we are using in our flow batteries, but then that's not all. So one crucial component related to flow battery is the stack. Within the stack, we can have several type of failure. Some have also, let's say, a direct impact on the chemistry or chemical risk, other not. For example, we can have mechanical failure, and in this case, I mean, the effect will be most likely leakage. This is a relevant problem for flow batteries, but can be managed through some mitigation measures as double containment, but it's something that has to be well evaluated since the design phase. We can have also balance of plant failure, like pumps or piping, and this can be managed in a similar way. However, we can have also off-nominal condition for the stack, and like hazardous voltage or current or isolation fault. This does not affect only the performance, but can lead also to formation of hazardous gases like hydrogen, for example, in some chemistry at least. So it has to be considered, and we need specific tests that assess this risk for each specific chemistry. So also the effect of this kind of off-nominal condition is strongly dependent on the chemistry, in the sense that in some chemistries, this will only affect, let's say, the hydrogen production. In others, we will have a degradation of the electrolyte that then cannot be used. So we need to assess well this condition that sometimes can happen even with a well-developed control system due to unexpected reason. Another point of attention is the environmental threats. These are of different type, can be impact even during transportation, can be flooding due to some extreme events, and external fire that can happen, of course. Fire in itself is not a risk for flow batteries, at least for most flow batteries. Of course, if we have hydrogen, that's a different matter, but for most flow batteries that are aqueous-based and liquid, with liquid electrolyte, that's not critical, but we can have an external fire that could create some threat, since we do have a fire load for the flow battery, although most of the battery, of course, is made of liquid, but we do have also the stack that contains also other components like plastics, like carbon-based material, and the effect of this, let's say, of the fire on this component needs also to be evaluated, since there is a possible release also as most combustion of any plastic material, or there is a release of possible toxic substances. And also the extreme temperature can have an effect, of course, on the safety, mostly because of the stack failure that can be caused by several, let's say, type of causes. The overpressure is one. This can be accidental, or it can be an effect of the use of the battery. Vibration, for example, to transportation before the installation and the commissioning of the system. Over temperature, this can be due to external condition, or even due to an off-nominal condition, so in case of overcharging. Of course, with aging as well, and after an intense pressure cycling, so after use in the end, it is also possible that there will be some leakage, and this needs to be well assessed by doing some test. Of course, from the regulatory point of view, in the last few years, there have been a very good, let's say, development on the safety standard for redox flow batteries. Since 2020, there's been the publication of 3 relevant standards for flow batteries applied to stationary system, of course. There are still some missing gaps. For sure, more detailed has to be performed on the stack level to assess the possible different cases of failure. And on the other side, of course, while the fire risk is not a major concern, fire, let's say, test on an entire system would for sure, let's say, enable to assess also the effect in case on extreme events like external fires. So there is still some gaps, but of course, all of these, let's say, the situation is much better for the chemistries that are already commercial, since a lot of this work is also done by the industry. For the chemistries that are still under development, of course, there is still a lot of work to be done, since the focus of research is mostly focused up till now on the performance rather than on the safety. But this is for sure a critical aspect for flow batteries that need to be assessed. Thank you very much. I'm available for any question that you might have later.